So let's do a little bit of arithmetic. For a reaction, standard energy for any change, so delta G at a given temperature, a different value at a different temperature. Well, how can we relate delta G and T to get delta H? And of course, the answer is the all-important equation, delta G equals delta H minus T delta S. Let's look at the two sets of data we have, the data at two conditions. Let's go first of all with the pink ones there. Delta G is minus 200 kilojoules at 450 K. Let's pop that in. Okay, minus 200 is delta H minus 450 times delta S, just popping that into here. Now let's think about the red conditions. Again, delta G minus 500, temperature 900. Pop those in there and we get this. Okay, now we've got to compare those and we see, well, we've got different values of delta G. Delta H we don't know, delta S we don't know, but we got 450 of those delta S's and 900 of those delta S's, and we really don't care about delta S in this reaction. So why don't I just multiply this whole equation by 2 to give me minus 400 is 2 delta H minus 900 delta S, and now I can combine those two equations together to get rid of the 900 delta S's. Various ways, of course, to do that conceptually. Let's just rearrange them each. So here we got 900 delta S, taking that over here is 2 delta H plus the 400. And then over here, rearrange it, 900 delta S is delta H minus, or plus that 500, because we brought the minus 500 over here. Putting those together, we get that because 900 delta S there, 900 delta S there. So 2 delta H plus 400 is delta H plus 500. Bring the delta H's together, subtract 1 from each side, so we'll have delta H. Bring the 400 over there, where it becomes minus 400. 500 minus 400 is 100. So delta H equals 100 kilojoules, of course. Methanol can be used as a rocket fuel. What are the signs for delta H, delta S, and delta G, respectively? Well, first of all, it's a combustion reaction. All combustion reactions, here's that reaction with oxygen to give the oxides, all combustion reactions are exothermic, so delta H is negative. Now let's think about delta S. We have 3 gas molecules on the left-hand side. We have 2 plus 4 or 6 gas molecules on the right-hand side. Okay, so 3 gas molecules going to 6 gas molecules. That's a nice increase in entropy, so delta S is positive. Now delta G, well, delta G is delta H minus T delta S. If delta S is positive, delta H is negative, then we got a negative minus a positive, which is an even bigger negative. So therefore, all of them are nice. It's a nice reaction in terms of delta H. It's a combustion. It's a nice reaction in terms of delta S. More entropy, and thus it's a nice reaction in terms of delta G. So another nice question in which we're thinking about a reaction, H2O solid going to H2O liquid, and we think about delta S, delta H, and delta G. Okay, well, delta S, as we go from solid to liquid, that's an increase in entropy, so delta S is positive. Delta H, what do you have to do heat-wise to turn a solid to a liquid? Well, you got to heat it up. So again, delta H will be positive. Now, delta G is going to be a variable. It's going to depend on the temperature. Okay, because what we've got here is we've got a nice delta S and a nasty delta H. So at low temperatures, delta H wins out, so delta G would be nasty. Okay, at higher temperatures, the T delta S wins out. In this case here, T delta S is nice as delta S is positive, so therefore delta G would be nice. So delta G non-spontaneous at low temperatures, spontaneous at high temperatures. Question is, of course, what defines low, what defines high? Well, sometimes you can calculate it. We'll be doing one of those in a minute, but otherwise just have to know your common sense. At room temperature, right, what happens to ice and liquid water? Well, liquid water stays where it is at room temperature, but at room temperature, ice melts. So in other words, it is a spontaneous process at room temperature. So delta G is nice. So the temperature at which it changed over must be lower than room temperature. And of course, you'll know what temperature that is, don't you? Consider the following situation: equilibrium. What happens to the ratio of partial pressure PCl5 to partial pressure PCl3 if the temperature is raised? Okay, and all we're told here is we're told the equation and we're told delta G. PCl5 is a righty, PCl3 is a lefty. So we're essentially being asked what's the ratio, right, at equilibrium, okay, to the righties to the lefties. Well, let's think about it first of all in terms of entropy, because as we raise temperature, the delta G changes, and it changes because T delta S changes. So we think about the entropy here. We've got two gases on the left, one gas on the right. So delta S is a negative value. Delta S is nasty. Delta S is less than 0, okay? And as the temperature is raised, this gets more and more important, okay? So it gets nastier as the temperature goes up. Okay, so nastier, of course, means it becomes less spontaneous, more non-spontaneous. In other words, it moves to the left. Okay, the reaction's going to the left because as delta G goes, temperature goes up, because you have a nasty delta S, you have a nasty T delta S. Okay, so if the reaction goes to the left, then we're going to be making more PCl3 and using up PCl5, so the ratio becomes smaller. Okay, so from thinking about the entropy, because it's a 2-to-1 reaction, two gases to one reaction going to the right, it's one gas to two gases going to the left. As you increase the temperature, you're going to go to the left because that's the good entropy way. How about enthalpy? Okay, well, what we know is that delta G is minus 92.50, which is nice, okay? And we know delta S is nasty. So the only way that you get a nice delta G when you've got a nasty delta S is to have a nice delta H. So in other words, the reaction is an exothermic reaction. Okay. Now, what do we know from Le Chatelier's principle when happens to an equilibrium when the temperature is raised? Okay, we know that as we increase the temperature, the reaction goes in the endothermic direction. Well, we've already decided here that the exothermic direction is to the right because delta H is a nice exothermic number. So if exothermic is to the right, endothermic is to the left. The reaction goes to the left, more PCl3, less PCl5. The PCl5, PCl3 ratio decreases. So fortunately, of course, you know, it's obviously not a coincidence in this particular case because I picked the questions, but both entropy and enthalpy considerations would indicate that the reaction goes to the left when the temperature is raised. Now we're doing some calculations. Given the following thermodynamic data, which the following statements describes the spontaneity of the reaction, blah, blah, blah. So we're given delta HF, heats of formation, and we're given S's. What can we do with that? Well, we can calculate delta H by simply summing up the delta heats of formation of the products minus that of the reactants. Remember, this is my version of your nice little triangles. All comes out to the same thing, but the nice thing of learning it like this is we can then apply it to the delta S, when I'm sure you have triangles for that too. So anyway, delta H, popping in the numbers, we got 3 H2s for which the delta HF is 0. We got 1 HCN for which the heat of formation is 135. We got a CH4 for which the heat of formation is minus 75. We have NH3 for which the heat of formation is minus 50. So delta H is endothermic reaction, 260 kilojoules. Now before I calculate delta S, let's think about it. We got two gases going to four gases, so I'm expecting delta S to be positive, which of course makes the overall question fun because of spontaneity. Well, if they're both positive, that's one of those that depends on temperature. But anyway, I get ahead of myself. Let's calculate delta S. Same idea, 3 hydrogens are now 130 because while hydrogen being an element in its natural state doesn't have a heat of formation, everything has an entropy. So H2 entropy of 130, HCN entropy of 200. Okay, it's a bigger, more complicated species, so you would expect it to have a higher entropy. And then both CH4 and NH3 have entropies of 190. So put all those together and we get delta S is 210. As we said, positive delta H, positive delta S. So delta G is delta H minus T delta S. Delta H is greater than 0, delta S is greater than 0. Thus, we know what our rules are, that the delta H wins out at low temperature. Delta H is nasty, so delta G will be nasty at low temperature. T delta S wins out at high temperature. It's a nice delta S, so it's a nice T delta S, so it's nice at high temperature, or spontaneous. Now, low temperature and high temperature, rather unsatisfying. Can we determine what the temperature is? Absolutely, because at changes spontaneity when delta G is 0. When delta G is 0, delta H is T delta S, or that temperature of change as we went through in the movies, delta H minus or divided by T delta S. Pop in those values, remembering that we got to have kilojoules and kilojoules, so it's not 210, it's 0.210. And we get temperature of 1238. So in other words, this reaction is going to be non-spontaneous below 1238 and spontaneous above 1238 Kelvin. Just like I said. For this reaction, blah, 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 telling you delta H is 100, so delta H is nasty. What's true about the relationship between delta G and T? Not sure why that completely is in there. I guess that's probably a leftover from when it was a multiple choice question. Anyway, and we know that delta G is 73 at 25 degrees C. So various ways we could do this. The way I would do it is I would use the data I have to figure out what delta S is. So delta G is 73 kilojoules, delta H is 100 kilojoules, T is 25 Celsius or 298 Kelvin. So we can figure out that delta S is 0.0906 kilojoules per Kelvin. Okay, so positive. So again, we got positive delta H, positive delta S. So we find out that delta G, of course, is 0 when T is delta H over delta S, just like we talked about in the previous question. So that temperature at which spontaneity changes is 1103 Kelvin. So in other words, the reaction, same as last, right? Under less than 1103 Kelvin, delta H wins out. Delta H is nasty. And so the reaction non-spontaneous. Delta G will be a positive number above 1103 Kelvin. At that point, the T delta S is winning out because it's a nice high temperature. Delta S is nice, so T delta S is nice above 1103 Kelvin. So the reaction will be spontaneous above 1103 with a negative delta G. Pretty much what I said. At 25, delta G is greater than 0. So if T is less than 11, delta G is greater than 0. If T is greater than 1103 Kelvin, delta G is less than 0. Nice, fun, graphical one. That, of course, as I've commented on in the live sessions, you're so good at graphing stuff. Correct value for delta G for a reaction that's spontaneous at standard conditions. Well, spontaneous, of course, means that delta G will be less than 0. So can we find a situation which delta G is less than 0? Okay, in other words, the products have to lie below the reactants. Well, that rules out B and it rules out D, but we are left with A, in which is below the reactants, C, in which is below the reactants, and E, in which is below the reactants. Okay, now delta G is that difference between the reactants going down to the products. Okay. So therefore, here delta G is between reactants and the lowest energy situation, whatever that happens to be. Here E, it's between that lowest energy situation and the products. Okay, so therefore the answer is A. Standard free energy. So defining standard free energy. So we look at making 1 mole of the HOOC-COOH, okay, and we make it from its elements in the natural state. Well, the natural state's here, and all nice pretty, I think, right? We got 2 O2s because we've got OOO, and the natural state of oxygen is O2. We need 4 of them, so we need 2 of those. We got hydrogens, we got 2 hydrogen atoms, well the natural state of hydrogen is H2, so I need 1 of those. And then we got 2 carbons, well the natural state of carbon is just carbon solid. You could get fancy with carbon graphite if you want, but I wouldn't be too fussed about it. Put all those together to get 1 mole of the HOOC-COOH. Let's see, we're given delta G of formations, and we want a delta G of formation, and we're told delta G of the reaction. So delta G of the reaction, just like the delta H and the delta S equations, is where we sum up the products minus the sum of the reactants. Well, all pretty colours. Delta G is minus 2879. In terms of reactants, we've got 6 CO2s, we've got 6 waters. In terms of products, we've got 1 C6H12O6 and 6 oxygens. Putting in the values, because of course we were told CO2, we were told water, we weren't told glucose, we weren't turned to oxygen either, but oxygen O2 element natural state, delta G of formation is 0. So rearrange everything, X, which is the delta G of formation of glucose, minus 910.6 kilojoules per mole. Determine the delta G of formation for the combustion one. So exactly the same question, except a nasty person that I am, I didn't give you the equation. That's okay. Heptane we know is C7H16. It's a combustion reaction, so that means it reacts with O2 to make CO2 and H2O. Balancing it out, we have to have 7 carbons, 7 CO2s, we got 16 H's, so 8 waters. Then we have 7 times 2 is 14, plus 8 is 22, so 11 O2s for the 22 oxygens. So now using the same equation, we've got on the product side 7 CO2s, 8 H2Os. On the reactant side, 1 C7H16 and 11 O2s. Pop in the values we're given, so CO2 minus 395, water minus 240, heptane plus 15, and again O2 0, wasn't given it. It is an element in its natural state, so its delta G of formation is 0. Plug all that out and you get delta G minus 4700 kilojoules. Quite a lot of energy from 1 mole of heptane, as you would expect, as there are 7 carbons there. Now we're into my favorite type of calculation, combining equations. So we've got an equation we're heading for, and we're given information about 3 similar equations and their delta G's. So the whole idea from just application of Hess's law, which applies to an awful lot more than just delta H, if I can combine these equations in some way to give me the overall equation, I combine in the same way the delta G's and I get the overall delta G. So let's make pretty colours, label them 1, 2, 3. Start off, I want 1 Na2O on the left-hand side. Well, I've got equation 3, but that has 2 Na2O, so I've got to divide it by 2. So that gives me Na2O, just what I want. Got an H2, don't want that. Got 2 Nas, don't want that. Got H2O, don't want that. So let's try and get rid of those. So for example, if I look at equation 1 has got an Na on the left-hand side. Well, I've got 2 Nas on the right-hand side that I want to get rid of. So I can have Na on the left-hand side, but I'm going to need 2 of them. So that gives me 2 Na, which are going to cancel out, 2 H2Os, where it gets rid of one of the H2Os, 2 NaOHs and an H2. So the H2s are going to cancel and the Nas are going to cancel. I've got this nasty NaOH, 2 of them I don't want, on the right hand side, and I've also got something going on with the waters. Well, let's go ahead and look at those 2 NaOH on the right hand side. To get rid of those, I want 2 NaOHs on the left hand side. Well, equation 2 has 2 NaOHs, but it's got them on the right hand side. So to get them on the left hand side, I have to take equation 2 and flip it. And when I do that, I get 2 NaOH plus SO3, that's the SO3 I wanted, goes to Na2SO4, that's the Na2SO4 I wanted, and another water. So now combining those, cancel out the 2 NaOHs, and I've got 2 waters on the left, 1 plus 1, or 2 waters on the right, so I can cancel them out, add it all together, and I get my final equation. So now for the delta G's. Well, I took the equation 3, for which the delta G was 260, but I divided it by 2, so that's 130. I took equation 1, for which the delta G is minus 146, but I doubled it to give me minus 292. And then I took equation 2, which was 418, flipped it, and so that becomes minus 418. Add all them up, the overall delta G, minus 580 kilojoules.